All right, so just to sort of summarize what we talked about yesterday with Newton's first law, the law of inertia. We know that the law says an object at rest will stay at rest. Okay. An object in motion stays in motion. But you have to remember that unless part. When don't objects stay in motion or stay at rest? Emily?
If they're acted upon by another.
Yeah, when they're acted upon by an outside force. So we have our tablecloth trick, which you yank tablecloth out from a bunch of objects on the table.
Did you do that?
Did I? I did it.
It was like a lemon.
Yeah.
Pretty cool.
Do it again.
You want me to do it again?
Yes. Pretty cool.
All right. Well, we'll add a little. Let's add some excitement to it.
Why? Because that's
Can you
glass.
do like a less?
Oh, and water.
Imagine if
We'll
it's
put
not
some
bad.
water in here.
Whoa.
What about a less heavy object?
Have you ever seen the Mythbusters episode when they tried to do it with a motorcycle?
Yeah.
Did it work?
No,
What
it
about a
didn't
paper
work.
cup?
No, because you couldn't accelerate fast enough.
So if I do this, well, I need some paper, I guess.
I couldn't accelerate fast enough with the tables.
Some of this non-durable paper that Dylan was complaining about.
I'm so scared because this is right next to me.
All right, so
I shouldn't have said that.
So the object at rest will hopefully stay at rest. Okay.
Do it again, do it again.
Do it again.
Now there are some factors here that will change sort of, this does not work well, okay, if you slowly drag the paper, okay? It also does not work very well if you have a, what kind of paper should you, or what should you not use here?
Paper.
We are using paper, Dan.
What paper?
Something like thicker.
Well, not so much thicker, sticky, what is sticky?
More friction.
Yes, a substance that would have more friction. You wouldn't want to use like a piece of carpet to do it, right? Because it'll be more friction. With a smooth surface, there's less friction between the paper and the glass, and so it's easier to slide out without that force of friction causing that unbalanced force.
Oh.
Yeah, but what if you did it like with a less,
Mr.
like
Mr.
really
Pull
light
it
one?
off the table slowly.
So the lighter the object, so the inertia an object has depends on its mass. So I'm not going to be able to do that same thing. I mean, maybe this is, but the lighter the object, the less inertia it has, the easier it is to get that object moving. Okay, and we'll talk more about that in our second law. But this is, I guess you could still do it.
But
You know,
have
if I
to
put a piece of string on there, again, well,
Could you do it with the one thing standing up?
This?
do it with the standing
Yeah.
up.
like that.
Yeah.
It'll probably fall because there is some, so even, this is not a perfectly friction-free surface. If it is, you can do it however you want. So there will be a little bit of force on that little hand sanitizer bottle. All right.
Get something really heavy.
No, I'm gonna stop now while I'm ahead. All my demos work perfectly, so.
No,
There.
one more.
All right, an object in motion stays in motion. Obviously, we talked about in our question today, Dan flying out of the car, Dan being pushed forward.
Like garbage can going fly.
Why is this guy lighting on fire again? I'm not quite sure.
I think it's funny. It's comical.
All right, so
The guy should do that.
No. I was.
does this work? These used to work.
Oh, who's
It's
driving
an
that car?
animated
Is Mr.
GIF,
driving
but
the car?
I guess.
Is it not? Yeah.
GIF can have 256 frames in it.
Wow. None of those work. That's unfortunate.
Wait, what do you mean? What?
There used to be animation, so this guy used to go like that. Same thing, this guy hits the brick wall, goes flying out of the car. So not that exciting. All right, let's talk about Newton's second law.
Ooh.
So Newton's first law, the law of inertia. Newton's second law has to do with forces and acceleration of objects. So the law states that the greater the mass of an object, the greater amount of force needed to accelerate it. Sort of common sense. Okay? And we have a formula that we use when we're referring to the second law. Formula is force equals mass times acceleration. So obviously, if you have two grocery carts that you're pushing, and you want to get them accelerating to, 5 meters per second, which one would you have to exert a greater force to get moving that fast? Yeah, the heavier one, the one with more objects in it. Okay, you'll need a greater force to make it accelerate. All right. When you guys go grocery shopping with your parents, how many times do your parents make you push the cart?
Yeah.
Sometimes.
No, my dad's like.
You ever smash it in the back of their feet and then they flip
Yes,
out?
yes.
They're like,
That's why he doesn't let me.
I like to ride little cars at Hanover.
"Oh, you go in the little car?"
Yeah.
No,
That's
I
great,
don't-
Emily.
I take
Your
it.
reference is going down.
always push it to the back there.
I take it.
Oh, without shopper and training sign?
I take it and I go sprinting down hallways and I jump on it and I just ride it.
All right, let's look at this a little bit. So,
Crashing new.
if I have my little
chair.
cart here,
Because I lost the car and right over my foot.
You go, Mr. Arcuri.
so we don't need Mr. Arcuri for this demo. So if I have in here a weight, and I put a weight on this end, okay,
Yeah.
and I release this, okay, so obviously they have the same amount of weight. If I take this out,
Do it.
so I have a force pulling on this car. Right now, the forces are balanced. What happens if I take this out?
Should fly.
Alright, so the car moves up the ramp, obviously, because of that force. Now, let's do it this way. What if I put another mass here and increase the force? Okay, it's gonna move.
Not all the way.
How, so what changed?
You had another mass.
Yeah, but, so how did that change what's happening to this car? There's a greater force, therefore,
And harder acceleration.
well, the car moved before.
The car moves quicker.
What if I add a third weight on here?
Oh, it'll go flying. No matter what
Alright,
you do.
Emily, come here, hold this. Redeem yourself, alright. Now I add a third mass here.
Wait, get that weight off and see if it.
No, alright, Emily, let go. Okay,
So the more the force. the
so the mass, if I think about my formula, thanks Emily. Did I change this about this cart? I did not change the mass. What did I change?
Acceleration.
The force. And so a greater force with the same mass results in a higher acceleration. Okay? Now, I can do this the opposite way.
Nothing will happen.
So if I have this cart,
No, and it's all the way up.
now,
Oh, you got it.
if I have I keep the force constant. So force is going to be the same throughout this whole demo. I have a certain mass. All right. So I have that acceleration. What's going to happen if I reduce the mass of the cart?
It's gonna go faster.
Right, because I have the same force,
But less mass.
okay? But now I'm decreasing the mass. What's going to happen to acceleration?
It's gonna go faster.
I want to see that final.
Yeah, can you like just let it go?
Yeah, put all 4 weights on one side and just let it.
Yeah.
It'll stop. That's not
Oh,
Put Mr.
wait, and then put Mateo's face at the
All right,
end.
let's see. Here's no mass. There's no mass in the cart. The only mass is.
It'll stop.
Please let it go.
Get the wheel
It's
off.
just gonna hit the pulley.
No, Mr. Arcuri though.
No, I'm saying like get the wheel off and just have it hang off the side.
What?
Alright, so
What?
you see how the weight, there's usually an on the wheel right now. The wheel
No,
thing,
no,
you can
can't.
just,
It's not the
pulley?
you're doing.
yeah, the pulley,
not
whatever you
really
want to
good.
call it. Unscrew that and
Now
have
let's
it
just do
go
this.
to the side. You can't, it's
They won't like pull
not
out
strong.
that friction.
Are you looking at what kind of hook?
All right, all four masses there. You want to see what's going to happen?
What, can you put Mr. Curie in it?
Sure.
Yeah.
Oh, that was.
So now we're going to be seeing a demonstration of both of Newton's laws, probably.
It's true! It's Mr. Arcuri.
All right, so
Mr. Oh! I don't care. With Mr. Arcuri.
Can you do it one more time?
Wait, can we invite Mr. Arcuri in here?
no, he doesn't need to know any of this.
Wait. Mr. Duras, could you could you put all four weights there and then just let it drop?
All four weights where?
In there. No, put them on the, down there.
On the cart.
Hey, I put Mr. Arcuri, wrap the string around Mr. Arcuri's head.
All right, so now we're getting a little.
I would say put the four weights.
Let's move on here. All right, now I'm gonna have you do some math. All right, so Mike's car has a mass of 1,000 kilograms, but it's out of gas. So he has to push the car to the gas station, and he makes the car go 0.05 meters per second squared. Using Newton's third law, determine how much force he's applying to the car. So go ahead. Why don't you calculate that out for right now, and then we'll talk about it. Yeah, take your calculator out if you need it.
What would be the label?
Good question. We'll talk about that in 1 minute. David, you got you calculating this?
No,
No?
but I got it right now, so no. Because I got 10 out of 4,000.
All right. So what's the formula?
We know it'd be 50.
All right. Force equals mass times acceleration. We know these variables. They're given to you in the equation. What was the acceleration?
0.05 meters per second squared.
0.05 meters per second squared. The mass was 1,000 kilograms. So what does that give you for an answer?
50.
50. Now the question becomes 50 what? So if you're combining units, you can do that. It's 50, not per meter, because we're not dividing. Kilograms times meters per second squared. Luckily, we have a shortened version. That unit has another name, a short name. It's named after a scientist.
Newton.
It is 50 newtons of force.
Oh.
So 50 newtons of force. 1 newton is 1 kilogram times meters per second squared. So if your units are kilograms and meters per second squared, then you can use newtons. All right, now just read the second problem. Bob, who must be going to a Grateful Dead concert, I think, is pushing his van. Same thing, he ran out of gas,
That or Bob Marley?
maybe.
He's dead.
Just think about it. What force would he have to apply?
A lot.
His whole body weight.
100 newtons.
Christopher? Why? How did you come up with that so quickly?
Because Mike's car was 1,000 kilograms, and Bob's was 2,000, and they had the same acceleration.
Yeah. So if you double the mass, you're going to have to use twice as much force to get it to the same, accelerating the same amount. And you could figure it out again. You could just think about it and figure it out. It takes 100 newtons of force for Bob to push his car.
Does it have to be a capital one?
Yes.
Why is everything exploding when it hits?
I don't know. So Newton's third law
Has 5 fingers.
is says that every action has an equal and opposite reaction. Okay. So Newton's third law is an important one as well. And so, you know, if you're boxing someone like that, okay, and you punch them in the face, you're applying a force to their face.
Yeah.
However, their face is also applying an equal force onto your hand. Okay? There's
Oh.
equal and opposite forces.
Is that why your hand hurts?
So right now, okay, if I push against this desk, am I applying a force?
Yeah.
Yes, but it's also applying force back at me. And now you could demonstrate this.
Well, what about when you push something?
What you are, it's also exerting a force. So if I take my rolly cart, we can demonstrate this. So when I push on this desk like I was earlier, why is nothing moving?
Because you're not strong
You're
enough
both
to move.
exerting an equal amount of
It's a
force.
solid.
But in a minute, I'm going to exert equal amounts of force and I'm going to move.
No.
Yes.
Well, it depends.
It's because you're not strong enough. You're not.
So now if I exert
No.
the exact same force, I do move. I didn't. The forces are the same.
Oh.
What has changed?
Oh.
David?
The wheels turn.
Okay. What does that actually change?
The force of the cart right now.
Friction between like you and the ground.
The friction. So when I'm standing here just on my feet and my shoes, I'm exerting this force, but this force is not enough to overpower the friction between my shoes and the floor. Could I push hard enough to overwhelm that force of friction?
Yeah.
Yeah, it's pretty hard. Okay, but you can. What does standing on the cart do?
Take away all your
It's
It
way-
makes the friction much, much less. Okay? So when I push with even less force, I still move in the opposite direction. So I exerted a force on the desk exerted a force on me, causing me to move backwards. Okay, so equal and opposite force. The harder I push on the desk, the farther I'm going to move, the faster I'm going to accelerate, because those forces are equal.
But like when you
Yes.
push on the desk, then like and it moves, say it moves, then are you putting more force than it has mass, or you're just
No, you're putting enough force to overwhelm the friction.
before your friction?
Yes. All right. So, you know, rockets, for example, jet propulsion works using this principle. If you imagine a movie out in space or even a rocket taking off, okay, you have ejected, when a rocket ejects, you know, gases from its propulsion system, it exerts a force. That is the force that actually moves the rocket forward. So gases are coming out of the end of the rocket with a high level of velocity, with a great force, but that force also is exerting, pushing the rocket forward, and that's why the rocket moves forward. If you imagine a hose, now not, you know, a fire hose or a strong hose, okay, or if you ever went, your parents wanted you to wash the car with the wand at the place, you have to hold on to that pretty tight, right, with the spray off one, because water is coming out of that hose at a very strong force, and that's exerting a backwards force that you have to control using your muscles.
Is that why like rockets, like before they take off, they normally like it takes them a second before they like leave the ground?
Yeah, it takes, well, for the force of that to overwhelm the mass of the rocket traveling up.
What would happen if the mass didn't?
It would not go anywhere.
It would explode?
It would just stay there, I guess.
So like,
It would be like a dollar store firework.
So Newton's third law,
I don't think they can legally sell it.
okay, if you ever tried to do this, if you're boating or on a canoe especially that was light, you try to jump off.
That really doesn't work.
So
oh yeah.
Yeah.
what happens to the boat? It moves away, right? Sometimes you send a flying, then you can't get it back if you jump off of it. Yeah, I'm not surprised. But you're exerting a force backwards on that, and that's what causes it to start moving backwards.
I thought the guy was gonna.
Also, so again, jet propulsion.
Why is he going through things?
So could Bob was getting tired pushing his van to the concert, so he decided he would put on rollerblades and make it much easier. Is that going to make it any easier?
No.
What's going to happen when he pushes it?
He's gonna go backwards.
He's going to go flying backwards. Again, that's because he's pushing on the car with 100 newtons of force.
You're not that smart.
It's pushing. Hey, I love Grateful Dead.
Never mind.
Wait, what'd you say?
Nothing.
Nothing. He's judging Grateful Dead.
You like
They're-
that?
Yeah.
I do too.
So they're exerting a force backward with the same level of force, but because the friction between his feet and the ground has been reduced, he's going to travel backwards. Recoil from shooting a gun. Okay, same thing.
Oh, it's painful.
There's the action of the bullet leaving the gun comes out with great velocity. It's not a lot of mass, but a great velocity. That exerts a backward force. Okay, they call kickback if you're talking about a gun. All right. What time is it over there, Richard?
Only 1 minute left.
1 minute.
Yeah, I can't hear.
I guess we'll have to watch this another time.